So I have both tapings going on, then we can compare. Okay. Oh, Rohit Meikani. Okay. So I'm also trying this Zoom.es, um, which is a pro version. I mean, they gave me a pro version. So let's see how this holds.
Did you have to pay for the
No,
pro
no, no,
version?
no. This was I didn't pay anything.
Okay.
This is supposed to be used by community college.
Okay.
So nope. I think somewhere. Oh, there you go. Zoom Pro account. That's what it is. And we can have up to 50 people in here.
Oh,
That's good.
wow.
So I don't want to have 50 people. I can handle 10, perhaps 15, perhaps. Okay, so 9:36. We are in. Good evening, everyone. I apologize for all these changes, but vacation is complicated. We do things, and next week, in fact, on Wednesday, I'm traveling. Thursday, I'm traveling. No, Wednesday evening, I'm traveling to Brazil. So I will be having a meeting next Monday somewhere in Brazil, and I try to make the time work because your 7 o'clock is gonna be 1 in the morning for me. If it's totally impossible, I we have to change, put it in a different time. But you guys are gonna be in school, so we have to talk. But basically, yeah. But
Yes.
welcome everyone. Today we have Pranati, and she's gonna talk about the Christian discs. And where's Pranati? I can't find Pranati.
Um,
Oh, there she is.
yeah.
All right, take it over.
Okay. Um, I'm going to share my screen now.
Okay.
Okay. So hey guys, my presentation topic is about magnetic fields around T-Tauri stars and how they affect accretion disks around these stars. So please stop me if you have any questions or corrections, and if I can answer them, I will, or I will definitely get back to you later. So here we go. Going over what was mentioned about 2 weeks ago, I guess, about T-Tauri stars. A T-Tauri star is a variable star, which basically means that random dimming or fluctuations of light are seen. There are generally 3 solar masses or less, which where like one solar mass is the mass of the sun. average age is about 1,000,000 years. They are generally F, J, K, M stars on the HR diagram, which tells us that these stars are actually pretty cool and are in reddish, orange, or yellow color. Their magnitude of luminosity ranges between 9 and 14, which means that they are hardly visible in the night sky. And so the lesser the magnitude, the more brighter they are for us to see in the sky. Accretion disks around stars. Accretion disks are basically materials that rotate around massive objects because of the gravity coming from the object, and they are generally made up of gas and dust. This material emits electromagnetic radiation, which is caused due to the viscosity of gas in these disks. Since the disks are considered Keplerian, the different annulus or rings rotate at different angular velocities, causing them to create friction against each other, and this friction in turn causes raising in temperature. Accretion disks of T Tauri stars emit mostly infrared radiation. And yeah. Magnetic fields of T Tauri stars. T Tauri stars usually have very strong magnetic fields. They have a magnitude of 500 to 1500 kg, and this strong strength is caused due to X-ray or radio emissions. And these fields are capable to pair or connect with accretion disks around them. So as shown in this picture here, you can see green lines. These lines represent magnetic fields, and they are being anchored onto the accretion disks. This anchoring or this process can concentrate the magnetic flux around the center of the inner disk, giving rise to even more stronger magnetic fields. Surface magnetic fields. This graph here shows surface magnetic fields being measured by the Zeeman broadening technique. The Zeeman effect is when light is in the presence of magnetic fields, individual absorption lines or emission lines in the electromagnetic spectrum are split into many different lines. The magnetic fields are modeled this way, and over here the x-axis represents the magnitude, and the y-axis represents stellar luminosity.
The boxes, what the boxes represent?
I'm not exactly sure, but I think they represent different particular stars.
And BF,
effects of these magnetic
that
fields.
BF, what that BF stands for in the previous slide?
Sorry?
And this BF on the figure on the left hand side, top right hand side, there is a BF.
So the left represents mean magnetic field
Oh,
strength.
magnetic field. Okay.
Magnetic field strength, and the left represents magnetic flux.
Okay. Oh, I got it.
Oh no, wait, I switched up. Sorry. The left represents the magnetic field strength, and the right represents magnetic flux.
Magnetic flux.
It's down.
And those are the numbers 3, 2, 1.5.
Yeah.
And another thing to add, the magnetic field of the star and the magnetic flux is pretty much related. The magnetic flux of an object is really the amount of magnetic field that's moving it through a cross-sectional area. So in that way, the magnetic field and the magnetic flux are directly proportional. And
right.
That relating factor is the area that the magnetic field penetrates through.
Yeah, so that's probably why you can see like these graphs look almost the same.
Right.
Right. Okay, so moving on. Yeah, okay. So the effects of these magnetic fields, the magnetosphere or the magnetic fields causes apparent control over angular velocity, and magnetic fields of such stars are thought to interact with the strong stellar wind, and this transfers angular momentum into the surrounding accretion disk. So this in turn allows the star to break its rotation rate as it collapses later on. The force from the magnetic field causes alteration in the accretion flow. Also, if the magnetosphere is dipolar, or basically if it has both poles, the north and the south, then the inner disk is truncated. So as shown in the picture, this is the star. The round mass on the left is the star, and the tiny chunks of black matter are the accretion material, and this is the stellar winds. The lines represent magnetic fields. The winds are pushing the material onto the star on the path or along the magnetic field lines. Conclusions: the accretion flow or push of material onto the star is caused due to the magnetic fields. It's magnetically controlled. Accretion diagnostics observed the stellar magnetosphere is inclined, which is relative to the star's rotational axis, which basically means the magnetic fields are also tilted like the star's rotational axis. And also to conclude, this topic is a really broad topic and is still being very much researched about. And many more simulations and research is still being done, and more thoughts and ideas are still coming up. But this topic is very popular because it is thought to have a lot of impact on future research as well. So yeah, that's my presentation.
Okay, very cool. Questions, discussions?
I hope everyone could hear me.
Oh yeah,
Okay.
I can hear you well. Any question? So the magnitude, if you go to the first of your slides or the second magnitude.
Mm-hmm.
So I mean, the magnitude we can see the visible stars we can see with the naked eye. Magnitude 6, if you are lucky. If you are in if you have very good eye conditions and the sky is perfect, no moon, no even Jupiter, 6.5 you can see up to there. So 9 you really need something else.
You need like a telescope or something.
Oh, absolutely. So most of the Tauri stars, those that were heavily studied, they were pretty much magnitude 13, 11, 12. So yeah, so 9, 14 is a good way of controlling them.
Right.
Depending on the mass, so you can have them as a Primem sequence phase, defined as T-Tauri star for up to 20 million years. That is a natural contraction time for a star that is M type of star or a K type of star. I mean, the contraction will take longer to be finalized in a main sequence phase. If you go on the next slide, another one, and now here, if you compare this nice picture that you brought here to the last one you brought it, so this young star, I mean, why does it have a strong magnetic field? So the only theory I think we have that explains the existence of magnetic fields not only in stars but also in planets is the dynamo theory, that magnetic field lines are generated if you have ions, if you have charge circulating somehow. So in fact, you can generate magnetic field lines if you have charge and you force charge into motion. So if you think about stars having first rotation, fast rotation, and second convection. So why is that? Well, premium sequence stars, as it was shown in the previous talk, is a star that is still contracting, right? So you have these big, giant molecular clouds, and then eventually gravity takes over and it starts to crunch and collapsing everyone. So eventually you have the center of mass rotating, and the rotation increases because of conservation of angular momentum. And the more contraction takes over, more angular rotation you are getting in your central star. So you do have rotation, you do have strong circulation of charges in there. But because the stars are low mass, then if you study the mechanism by which energy from the center part migrates to the surface, you can have, for instance, radiation carrying energy. That's one mode. But you also have convection. So convection is a mechanism by which hot material rises up to cooler regions and transfer energy. So convection is efficient in low mass stars like T-Tauri stars. So T-Tauri stars, you have both mechanisms. You have convection and you have circulation, which means rotation, fast rotation. And this generates this global magnetic field. They are pretty much nicely represented in one of your last slides. But these blue lines over here, they don't stop in the disk. They are not anchored in the disk. Remember, magnetic field lines, they don't start and end in a point. They circulate. For instance, if you were to draw a magnet, let me see if I can do with annotating. Let me see if I can do that. Pranati, can you, let me see, how can I do that? Let's see if I can annotate somehow. Just a second. Annotate. I think I can. Oh, I can. That's pretty cool. So look at this. So if you were to draw magnetic field lines in this star, would it be something that comes out of there, goes down, uh, uh, goes into the disk, and then down, 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 and then go back to the star and then closes up. See that? So the field lines is all closed up. Yeah, I don't know what I did. Let me see if I can do it again. Yeah. Can you guys see that?
Yeah.
I don't know why it changed position. Where can you see a red circle I did?
Yeah, we can.
But where is this red circle? I can see it's outside the star. It shouldn't be outside the star. I don't know why this happened. It should be something like this. Let me see if it's gonna go away. No, it didn't. That's cool. Let me see now. Okay, back. Oh, it stayed there. Okay, so magnetic field lines, they circulate and close in themselves. So if you go to the last picture you show, if you can show quickly.
Or the previous picture?
No, the last one. I think it was the last one. That it had a frontal view of a Christian disc and a central. No, yeah, that one. Now, let me see. I have to erase this. I guess so. Wait a second. Eraser. Eraser. That's what I want. It's not erasing. Oh, yes, it is. Takes some time. Okay, so here the same thing happened. You have your field lines, right? Come somewhere, and then wait a second. No, I can't annotate. Why is that? There you go. I think I will be able to do now. Okay, so you have a field line that goes like this and then goes into the disk and then down and closes up. Now, this disk, as Pranati mentioned, is a Keplerian disk, which means so a blob of gas that is circulating at this radius. I mean, as time goes by, this blob goes all around and then back, and then little by little, it migrates towards the central star. So a field line that goes into the disk, it collects some ions, right? Because ions get frozen by magnetic field lines like pearls in a necklace, and then eventually the disk, the gas, brings these field lines towards this region that is associated with a region that rotates at the same rate as that of the star. It's called corotational radius. So then you have all this concentration of field lines here. Can you see that? All pinched, all concentrated. So the flux is pretty high at this location right here. And because of that, then the field becomes efficient enough to drag material, to take material out, and then drags and then shoot it towards the star, towards the center star. I don't understand why when I annotate, my marks get all over the place. This is something I have to ask them, why am I happening this? So I don't know. But then you see this blob over here, this black thing. This is a hot spot. It's a region of high temperature as a result of this gas that falls onto this region. So if you allow the star to rotate, you would see a modulation in the stellar brightness caused by this spot coming in and out of view as you observe the star. So if you are an observer, that is somewhere here, let me see, options, annotate. So if you have your viewing position right here, right? So then sometimes you see the spots, sometimes the spots come out of view and then back and then circulate that way as the star rotates. Does that make sense? Kind of?
Yep.
And one interesting is that if this part represents the disk right here, so the disk is not meeting the star, right? So we have a gap between the disk and the star itself. So we don't have star following on the stellar equatorial region because the magnetic flux, the magnetic field kind of prevent that from happening. Okay. Let's see if I can. Oh, somebody has a hot music in there.
Oh, sorry.
So I don't understand why my marks are all over the place. Yeah, I don't know how you guys are seeing, but I'm seeing all over the place. It's funny.
Yeah. Would it help if I stopped sharing and I could send my presentation to you?
No, don't worry. I think
that would be better because it's kind of laggy on our sides.
Can you guys are having all over the place as well, right?
Mm-hmm.
Yeah.
Yeah. Well, and the last slide of yours, and just see quickly. Yeah, that's true. So you have a lot of work done that needs to be done, and we have some data on this type of stars, and I have to recuperate that. That would be some interesting thing to do. Besides the Kepler data.
To also add on to what Mr. Batalha talked about, so he previously mentioned something called the dynamo theory.
Yes.
So basically what that is that it's kind of like a mechanism in which you have fluid motion in the Earth's core, specifically the outer core, and that fluid consists of like a molten iron, liquid iron, and that iron is moving rapidly as the Earth rotates. So you have a rotating core, and because the iron is basically just plasma or like lots of ions just moving around. Those ions generate a magnetic field, and as they increase in speed, as those ions increase in speed, the strength of the magnetic field also increases as well. It's also for this reason that when you look at Mars, it has absolutely no magnetic
Yeah,
field,
very weak magnetic field.
or a weak one.
Yeah.
But I think it was, I forgot what satellite was, but we did some measurements of like remnant magnetic strength of like remnant magnetic pulses or stuff like that, and we found traces of those remnant magnetic fields. And it turns out that Mars used to have a magnetic field once. So yeah, it used to have a core that was rotating very fast, but for some reason it froze. And we probably think that like an asteroid may have hit Mars, and that may have caused or to stop rotating.
Yeah.
And then it slowly lost its magnetic field.
A telltale of a magnetic field in the planetology is rotation. That's true. So yeah, so Jupiter has a fantastic magnetic field because it rotates like a maniac, and in addition has
5 hours a day. 5 hours.
And metallic hydrogen. So you have an ionic circulation, and then you have all these global magnetic fields being generated, and objects that are probably geologically dead, like Moon. In addition, without rotation, Moon doesn't have the ions that would generate magnetic fields, nor has a fast rotation. So you don't have both, and so Moon has no magnetic field that's significant. Earth has some because Earth has a molten core, as Sean mentioned. So when we tackle these Primian sequence stars, even Herbig EEB stars, for instance, Herbig EEB stars, they are not supposed to have a significant magnetic field as a result of they are hotter, they are more massive, and they don't have convection as robust, as efficient as low mass stars. So they rotate fast, but they don't have convection, and so the dynamo is not necessarily efficient in the star. But there are indications that some Herbig EB stars do have magnetosphere, and they do have certainly circumstellar disk. And then one line of investigation that is still open is to find out if the magnetosphere is strong enough to truncate the disk and disrupt the disk as it happened in T-Tauri stars, and do all kind of these cool hot spots that we observe in T-Tauri stars. So we have some data, but we have to recuperate that. Talking about spots. So how did you guys face the spot challenge?
Oh yeah, so we haven't technically started on it.
Okay.
But now that school's about to start, I think it would be a great time to get together and start working on it. I have the instructions with me on my screen right now, so can I share that?
That would be wonderful if you could. I almost asked you, but I decided not to because it would be too abusive. But if you could put together all the chat we had over the phone in a document and send to everyone, that would be great.
Wait, put what?
All the chat we had over the phone.
Oh, okay, sure.
I don't know if you can do that in an easy way, but that was pretty nice. And also, I mean, the idea is in a regular star like the sun. The sun has small spots, but this premium sequence they have bigger spots, and then you can use these spots to determine the orbital, not the orbital, but the rotational period of these stars. Now, in this premium sequence, the so-called classical T-Tauri stars that I think was Philip who mentioned that, the classical T-Tauri stars have these accretion disks, and because of these accretion disks, they also have the hotspots. So the hotspots would modulate the stellar brightness in a way that's different from the the cold, dark spots, because it would drive the brightness to a higher level than when the star has no spot at all. So it would be some interesting line of investigation to just once you can solve the problem for a flat star, what if you change the spot from a spot that is 3,000 degrees or 2,500 degrees for a star of effective temperature 4,000 degrees? What if you go now to 9,000 degrees, and what would be the difference um, on that? And then we could go to real data and try to see if that makes sense.
Okay, so let me switch over to my screen. I have the instructions in front.
Yeah.
Okay, I'm gonna stop mine.
Okay.
Thanks, Pranati.
Thank you.
So here we go. Do you guys see the instructions?
You have to move to the left.
Like how?
I don't know how. I don't know because you have a half of my screen is empty and the other half is the document.
Really, that's weird.
Yeah.
Does anyone else see?
No, it's fine for me.
It's fine
Yeah,
for
same.
you? It's just for me? Oh, that's no fair. Okay, you see the entire document?
Yeah, the entire document. Can you guys see the entire document?
Yeah, I can see it.
I have Radio Astronomy Research Project 2016 Google Drive. And then below that, I have, now I can see Gavart, student.
Yeah, so
And when you open the document is only in half of my screen. How funny.
that's weird.
That's weird. Let me see if I can
But I
read
think I
some.
sent the instructions to you anyway, so maybe you
Okay,
can open.
so don't worry. So if everybody's seeing okay, that's fine.
So, yeah.
Yeah, sorry, but was this shared?
No, I'm going to do it today, like after we are done with this.
Okay. Okay.
So yeah, like for the past week, I've been working on the instructions for this. I've been talking with Mr. Batalha about like how we should proceed with this project.
Sean, can you call me Celso instead of Mr. Batarra?
Okay.
Call my first name. I'm calling you guys for the first name. Yeah, let's set the ground. We are all in the same ground.
Okay.
Just having fun.
Sure. So this is the mini project that we're going to be working on for, I don't know how long it'll take, but hopefully we should be done with it in the next month. Hopefully. Anyways, so I think this project will mostly be based in EV since nearly all of the people who come to our meetings are from EV, and honestly, that's actually pretty good. Like that's for the better because that makes setting up our meetings a lot easier. Like we could just meet up at school and work on it there. So yeah, so let's get started. So basically, we're gonna consider a star, right? It's going to be a flat disk, a flat rigid body. It's gonna have a certain temperature. We're gonna call that T star, and basically, it's the effective temperature or the average temperature over the entire photosphere, which is basically the surface of the star. And this star emits a total flux, which is called F star, and that is equal to sigma T to the fourth power. So this is an important equation that you have to know. Flux is always related to the temperature by the fourth power.
Yeah.
And this constant here is called the Stefan Boltzmann constant. And it's equal to 5.67 times 10 to the power negative 8. Let me just check that to make sure. Boltzmann.
Yeah, the flux, you would have to integrate that over the entire surface area. So you have a term there that which I'm not even worried about it, 4 pi r square. When we go to a spherical star, right now it's a flat star, right? It's just a disk. So I thought, okay, let's just work with sigma t4, but in reality, you have a 4 pi r square multiplying that term.
Yeah, so those are all the other complexities that we'll get to later after we start the initial project.
Right.
So basically, that's the flux of the star, right? Basically, what the flux says is that the star emits some amount of power per some area. So basically, it's in units of watts per meters squared, right?
Right.
So the farther out that you are from the star, the less energy that you get from the star.
Yeah, less you collect, correct.
Right, and another important thing to know is that the luminosity of the star remains constant at any distance that you're at. So yeah, and now let's just say that we have a sunspot that comes into the picture. Again, this sunspot also has a certain temperature. It's not a complete black body or anything like that.
Right.
Or is it? Are we assuming that's a black body, Mr. Celso?
Yes. Yeah, we assume the spot is just to make it simple. The spot, if you observe just the spot, you have you could mimic the spot by the gas of a cooler star. Let's say a star that is 3,500 or 3,000 degrees, bunch of molecules, because the gas is cold. It's just a gas with a low temperature.
Yeah. So it's just gonna have a temperature. Usually, the temperature of a sunspot is a lot cooler than the effective temperature of the star. And that's because it has a darker color. We can just tell by looking at the color of the spot. And this spot occupies a fractional area of delta. So that's just area of the spot divided by area of the star, right?
Right.
And if that's the case, then what we should really be seeing for our total flux is this equation over here. Looks pretty complex, but it's not. So let's try to break it down. So let's look at this part. 1 minus delta times sigma t to the fourth power of the star. And this is the photospheric emission. So I'm going to recreate the scenario. So here we have the star, right? And then here is our sunspot. Let's just say that this star has a radius r, right? And this little spot has a radius little r, right? So then the area of the star would be a star equals pi r squared, right? And then the area of the small one of the sunspot would be 8s, which is equal to pi little r squared, right? So, and then if we take the ratio of those two, a star to as, we get our delta. So our delta is basically just r squared over big R squared. Now the reason that we multiplied this entire thing by delta is that we basically just covered our entire star by this one little spot here.
Right.
So really, we're missing that this little flux, like this little chunk of flux that would be coming out here, but is now covered by the sunspot, right?
Right.
So basically, the area of the star that's not covered by the sunspot is 1 minus delta, or that's the fractional area of the star that's not covered by the sunspot, and that's how we got this part here. So we're saying,
can I step in quickly?
Yeah.
Okay, in this figure here, that's pretty good. So let's say this spot is 10%. 10% of the stellar area, 10% is the spot, right? So if 10% is the spot, so the star photospheric emission is going to be 90%. So 90% of the flux photospheric, which is sigma T photospheric to the fourth. So 90% of that comes from the photosphere, and 10% will come from the spot. Does that make sense? So you have 90% from the star, 10% from the spot. So then you have altogether, you have 100% emission from the entire star, but 10% comes from the spot, 90% comes from the star.
Yeah. So basically, we have this part of the star, excluding the spot, generating a flux that's proportional to the star, to the temperature of the star, right? And that's how we got this part.
Yes.
Right? But the sunspot is also has its own temperature, so it has its own flux.
Yes.
So it's generating its own flux.
Yes.
So that's where this part comes in.
Yes.
And that's the spot emission.
Yes.
So we have two different fluxes in play, one from the star and one from the spot. So do you guys get that? So not all of the star is generating its own flux. Only the part of the star that's not covered by the spot will be generating the flux that's proportional to the star's temperature. And then there's also the spot that's generating its own flux, and it's proportional to the temperature of the spot. So is everyone...
You could take a kind of a extreme sort of a thought, like, let's say the spot is as big as the entire star, which means delta is 1, right? So it's a star that is just one spot. So if delta is 1, the flux here of your photospheric emission becomes 0. 1 minus 1 is 0. And then the entire flux you have is the flux from the spot. But that's true because the spot is the size of the star by assumption. By the other token, if you say, okay, there is no spot and delta is 0, then your observed flux is the flux of the star, the photospheric flux.
Yeah, so that's why we got this equation. So is anyone else confused, or can I move on? Should I move on?
Are we all good? I think everybody's sleeping.
Oh, yeah.
Oh, they are there.
Okay.
All right.
So moving on. So yeah, we kind of like explained it here. Without the spot, the observed flux would be a sigma T to the fourth power of the temperature of the star to the fourth power. Because if delta is 0, then then the flux caused by the sunspot, it goes away. So we kind of cancel that out, and we're left with the photospheric emission. 1 minus 0 is just 1, and we get sigma T to the fourth of the star. So yeah, cool. So now, basically, we're going to consider a star that has a radius r star, right? And then it has a temperature T star of 5,000 Kelvin. That's like around the temperature of our own sun. Some PMS stars may be around that temperature as well. And this PMS star rotates every 5 days. That's pretty fast. The sun rotates around 27 days for every rotation. And then we have a star spot with a radius r spot that's equal to 0.1 times the the radius of the star. So it's 1/10 the radius of the star, and has an effective temperature of 3,500 Kelvin. Right, so that the star spot is a bit cooler than the surface temperature of the sun. So for now, we're going to assume that both the star and the spot are flat. So in a way, you can kind of treat this like if you were to you can probably treat it like a transiting planet or something, but except it's on the surface of the star, right? So it's like moving from left to right on a flat disk. So as the spot enters through the star's limb and makes its way across the surface, the observed brightness of the star changes. Right, so this kind of makes sense. So here you have a star with no star spot, so it has like a stable flux. But then your sunspot or star spot starts to move in, right? And then that kind of causes the flux to decrease in strength, and then eventually the whole sunspot makes its way into the surface of the star, and for now we have a stable but lower flux as it makes its way across the sun or the star. It exits the star and the flux starts to go up because the area of the sunspot is decreasing as time passes by, and then eventually we're left with no sunspot once again, and the flux returns to its normal value.
Yeah, the brightness goes back to the normal.
Yeah. So basically, the goal of this project is to create a program using Python or some other program or some other program, if you guys are interested in others, that tracks these flux changes given the conditions that I just talked about. We can try to have graphics if possible.
A little bit of a challenging will be, I think you guys can do well setting up a limit for the continuum flux. So you just take a TF of 5,000 degrees and then you have a number in there. And you can also find out well for a given stellar radius and for a spot, let's say 10% of stellar area, a spot of 10%, you can also determine the bottom of this dip. The question is, how are you going to time this downflow or downfall in flux from the purely photospheric flux to one that has a spot? So this little transition here, how are you going to determine that? So one of the suggestions is, so let's say you have a spot that is 10%. So what if you allow this entire area to migrate into the stellar disk in a linear way? So make it something simple. So let's say the star has a diameter of 10 units, and my spot has a diameter of 1 unit. So which means and my star rotates in 5 days. So a spot that is 1 unit would take 5 days to complete a whole turn back to the same point. So how long would it take for that unit to go into the stellar disk? Since the first moment it appears in the limb, how long would it take? Because if you can answer that question, you would be able to find out what would be this transition, this downfall from stellar flux or photosphere to the one that has the spot and the star together. So basically, the picture where you have the spot next or at the limb, this is the challenging of this project, is how you're gonna resolve that.
Right. And for now, we're going to assume that the spot enters through the equator, which makes our calculations a lot easier.
Please simplify. Yes, absolutely.
But eventually, we'll add in like all of the other stuff to
Yes.
make to let the program accommodate for all of the latitudes.
Yes,
And
and more so for T-Tauri stars in a dipolar field, you have not a spot in the equator, right? The spots are at high latitude, and it's not just one. You have two. You have one on the top, pretty much close to the North Pole, and you have another hot spot close to the Southern Pole because it's a dipolar configuration. So you have the two poles pretty much with a hot spot sitting on them. So when one spot comes into view, probably the other one is come out of view. You have this dancing going on, and would be cool to see what type of curve you would come out.
yeah, so basically, sunspots kind of serve as like a source for most of the magnetic fields that we see on the sun or the star. It's our star.
It is a dipolar one.
Yeah. So
Yeah.
usually when we see a sunspot, there's usually another sunspot like either on like the near the opposite pole,
Yes.
and then you usually see like magnetic fields that come around like that.
Yes.
And also, and yeah, so they share this dipolar characteristic, and that's also something that we may need to take into concern into account because these two sunspots may be interacting with one another, and they could affect like how fast these sunspots travel on the surface.
But let's see. Let's say your star rotates like this, right? But your dipolar configuration is like this. Go like this. So you have a spot here, and you have a spot there. So this is a hot spot. So you have another hot spot here. Okay? And let's say you are here. You're observing from here. Okay? So now you see your photosphere and you see a spot at high latitude. And then the spot rotates. When the spot is here, the bottom or the southern spot appears on view. So your light curve is going to be something weird. It's not going to be the simple thing like this, You're going to have some double type of spots coming in and out of view. And not forgetting you have a something like that. So it's a little bit more complex, but yes, you should start with your equator. By the way, can you see my annotation going on?
Yeah.
Yeah. So you should start with the equator and solve this part, and then you are happy with it. And then another one, okay, let's see what happens if I put a stop right here, a spot on the top, let's say a 70 or 60 degrees latitude. Then you see what happened. So what happened if I now have a dipolar configuration, and instead of a cool spot, I have a hot spot here and a hot spot there? What would be the result? But then you would have enough skills to resolve that, And then the last one would be, okay, let's put my observer at any particular viewing point. So I could have an observer here, I could have an observer some other position. So those different observers would see it. I mean, the periodicity would be the same, it wouldn't change, but the characteristics of your light curve would be different.
Mm-hmm. And yeah, and then like other factors that we may also have to take into account of is like what Mr. Patel had been talking about is the differential rotation of the star. So usually,
oh my gosh, it's gonna complicate like a hell.
Yeah, but I mean, like we could try. I don't know if we may have time for that, but it'd be cool to see. But I guess it's worth talking about it now. So for this project, we're mostly going to assume that. Oh wait, there's a bunch of annotations here.
Probably I'm the one who needs to erase them. Wait a second. Yeah. Or so, can you get a different page?
I don't know. I could probably just move it.
Okay, I'm erasing.
So for this project, we're just going to assume that the star is basically this rigid, flat object, and then we can probably like move on from a flat object to a spherical object, and we might also have to take into account of the 3D part. But for extra, should we ever have time, we could also take into account of differential rotation. That may require a lot of research, like some degree of research, before we can actually like start programming that into our code. But basically, when I say differential rotation, so remember that a star is basically made up of plasma, like ionized gas and all of that. It's not a solid rocky object like the Earth, for example, right? So usually at the equators, you'd have gases that are going at around 25 days per rotation, but then you'd also have like these gases around here that are moving. Wait, is it a faster or slower rate?
Right.
It's faster.
It's faster. No, it's
Slower.
a slower. So it's
Yes.
faster in the equator.
So at the poles, it's a bit slower, and that's what we mean by differential rotation. So as you move up in latitude or down in latitude, the rotational speed of the sun starts to slow down. So it's faster at the equator and slower at the poles. So that could also affect like the transit speeds of our star spots, and that's maybe something that we should account for, but we may not have to worry about that too much.
Well, but when we get to that point, in about a month or month so, I would like you guys to be having your hands dirty with data and play around, because yeah, it's fun. It's really fun.
Yeah, but for now we're just gonna start simple.
Yeah,
Just a
please.
flat rigid body, a flat sunspot,
Yes,
and once we get that working, we'll work our way up
yes,
to stuff like this.
yes. Let's go have fun. I mean, let's make something that we are proud of ourselves, but it's simple.
Hopefully it doesn't sound scary. It'll definitely be a lot of
Yes,
fun.
yes. Very good.
Yeah, so
Okay. The other thing is, I'm putting all this taped material in my YouTube channel. If I forget to upload for some reason or send to Sean, you guys can pick it up there. So, but I'm taking this tape and just put it in there
right.
if you want to review later.
So do you guys have any questions about this project? Anyone?
Do we have any times you plan to meet up?
Hey, Thomas, is that you?
Yeah.
Hi,
Can
now I
you-
can hear you.
Oh yeah, what was your question?
Do we already have a planned time to meet up?
So are you from UBC or?
I'm about to be attending EVC.
Okay, so I would as I mentioned before.
I can work with Thomas. Don't worry.
Okay, that's great.
Yeah, you guys can work at EV. I mean, let's use our resources. I can communicate with Thomas. There is another fellow, and he's not logged in today, but he went to the observatory. By the way, this Friday, there is observatory. If you guys could go there, would be great. And somebody's gonna be talking about asteroids, asteroid impact. The guys from SETI. I will send information to you guys. But if you could go, that would be great. So there is a talk on asteroid impact, and then there will be the night viewing. But I can work with Thomas, and there is another fellow, Surinder. I think that's his name, and he is volunteer in the observatory, and he's good in computers, but he's not having time to join the group yet. But he's another resource, and but I can work with them. Don't worry, Sean. If you can get the EV people together, that would be great, and I can work with Thomas over the email.
So what I'm thinking of is having our meetings maybe after school. You guys could bring your laptops and all, and then we could like get together, start like discussing how our program should be like, and whether we should like implement graphics and all that. I think we should. It'd be a pretty good, useful thing to do. And then like if necessary, I could also like host our meetings someplace else so that people like Thomas and other people from EVC or other schools
Yes.
could join us.
Yes. I think the idea in the future, if we get funded and if everything goes according to what we are thinking should go, we would have these different projects going on with different groups. And every 2 months or so, we would get together in a whole day workshop. And then the different groups would make presentations of what the status of their particular project, and then hear from everybody else, and then everybody else would jump in with suggestions on how to improve their own development. So that's the idea. So we still could have that. For instance, I could work with Thomas, Sean, like I work with you, replying emails and text messaging. It works. I mean, it's so efficient. It works so well, and then we use our free time to have fun. That's the whole point.
Cool.
All right.
Um,
Is that
any
okay,
questions?
Thomas? Can you work with me that way?
Yeah, should be fine.
Okay, very good.
Yeah, and we can keep in touch with each other on our progress.
Okay.
Wait, Sean?
Yeah.
Wait, can you share like all the docs that have to do with like the project?
Yeah, I'm gonna share these instructions through the group. I know. I've also created this one EV group that I've never used at all. So now would be a good time to use that group. And I'll also be sending them out through email, not just to you guys, but to everyone else in the program, like from goals and all. Should they be interested?
That's a very good idea. You are giving a good suggestion. Let's say Sean and EV people have their own web page or Facebook account, and you guys can develop the projects as you guys are developing now in their own way. And let's say Thomas and perhaps Surinder or somebody else from Evergreen Valley could create their own media center to exchange information and upload the data and documents as they progress in their own project. Perhaps Thomas, we could talk about organize something like that.
Okay.
All right.
So, how many people do we have here who may be interested in working on this project? I'm guessing that would be all of you, but I just want to make sure that all of you guys here can work on it, like for the next month.
Yeah, I'm good.
Yeah.
Okay. So, if you guys have anything that might prevent you from working on this project, just let me know, and we can work out something.
Very good. Very good. I think we have on sometime. And Thomas, we communicate. We can talk.
Okay.
You could have my cell phone. Let me write here. So take note because it works. Right now.
I had a quick question.
Yeah.
What is the purpose of this project?
The what?
What is the purpose of this project? Is it just for us to understand, or
Just basically to understand.
okay?
So all of these seminars that we've been doing, hopefully, like stuff that we've been learning from those seminars might help us in this project.
Right. Okay.
So these stars, they show variability in their photometric light curve, which means in the brightness. And this change in brightness is pretty much due to these spots. In the classical T-Tauri stars, those with these heavy accretion disks, the spots tend to be hot. And in weak T-Tauri stars, like those weak Phillips mentioned, the spots are big, but they are cool spots, like the sunspots. So it's a different sort of a physics. But for classical T-Tauri stars, in addition to do photometry, we also do spectroscopy. And in spectroscopy, now, if Pranati can show her the second slide. Pranati, are you still there? Is Pranati there or she left? Let me see if I can pull up Pranati.
Sorry, I'm here.
Oh, you're there? Can you?
Yeah, I was talking and I forgot that my mic was on mute.
Oh, no worry. Can you show the second slide of your presentation?
Sean's sharing his screen right now, and I cannot share mine until. Okay.
Okay. All right.
Yeah. Okay. So.
All right. I think it's the second one.
This one?
Yes. No. Move on. Another one. Could it be this one? Another one. Is that the only picture I have?
Yeah.
Well, okay. So here, see this. Let me bring an annotation here.
Is it this one?
Let me see. I don't know, but I can use this one. So
Okay.
Here in this region, can you see this red dot that I'm making?
Yes.
Okay. So this red dot, it's inside a funnel, which is like a big bottle in which the glass is magnetic field. Now it's moving again. I don't know why it gets so. See, this red blob is supposed to be in the funnel and is following towards the star, right? And now, if you have a observer sitting right here, oh, my annotation gets all over the place. Let me do something different. Stop for a minute sharing your screen.
Okay.
Yeah. Okay, so then you have the star. Oops. So you have the star, and so you have the disk that is truncated somewhere here. We have global magnetic field, and then somehow here gas is taken out, and then there is a big chunk of gas being levitated, and then eventually following right there. So let's say, and then you have this big spot. So take a cell of gas right here. This gas is falling. So if you look from here, which means you have your telescope on planet Earth and somehow in this direction, you see this gas falling towards the star. In other words, the gas is moving away from you. So if you do spectroscopy, so let's say in the photosphere or in the chromosphere, let's say some emission line would appear like that. Now, if it's moving, this is your blue end, this is your red end. Now, if this blob of material falls towards the star, you should detect this emission line to migrate a little bit towards the red. So you have some red shift going on. And as the star rotates, right? So eventually now the lower part of the star, you might have the spots in which the gas now falls towards the star, and you might be able to see that falling star going towards you. So after half period of rotation, you would be able to detect some feature that is blue shifted. So if you have this dipolar configuration, and if you do spectroscopy, you might be able to detect during a rotation period one red shift feature and one blue shift feature, all of them with this periodicity associated with the stellar rotation. So you see how the project can become complex as long as you have sufficient data. You can pretty much do very nice job. But again, it all starts with this simple project of yours, and the project is what happened with the star brightness if there are spots and if the star rotates. So how can I learn and create some skills that help me to interpret this type of data? So then we make it more complex. So let's put double spots. And so what would happen with the star brightness? And in a later stage, so let's now thinking about the circumstellar material that is falling towards the star or even being expelled in a major wind. So what sort of a feature should I be able to observe in my data? But this is a very long shot, way in the future. And of course, this is supposed to be done after you are completed with your homework and your grades in the school are awesome, because you can't go anywhere in science if your grades are not good, right? That's the whole deal. Okie dokie.
So, any other questions about what Mr. Patala talked about, the project in general, or Pranati's presentation?
I have a quick question about Mr. Patala's drawing.
Yeah.
So is the matter falling into the dark spot to the star's north matter ejected from the sunspot on the star's south that loops around and then falls back in the north?
This spot is a hot spot. It's a hot spot, and this material is being dragged out of the disk. So you have a disk here, which I'm not depicting, but you have a disk that is circulating the star, and the magnetic field of the star is so strong that it's able to disrupt the disk at certain location, so that the gas disk does not meet the stellar equator. So on the contrary, it's dragged and levitated by this magnetosphere and then take it towards the stellar surface in these mega shocks.
Okay.
All right. All right, fellows. Time to sleep.
Okay.
Very good. Good presentation, Pranati. Make us think about all this data. And
Thank you.
very good. So next week, who's on charge? I don't remember who was in charge next week. Oh, Rohit. No, who is next week?
Gaurav.
Okay,
Oh yeah, Gaurav left the
go.
meeting early.
It's frozen for me. It did for me as well. So is it freezing? Is there or I can't see anything. Oh, okay, it's better now. All right. Okay. Good enough. Good night, you guys.
Best tomorrow.
Thank you.
Good
Good
night.
night. I will process the video and put it in my channel.
Okay.
Okay, bye.
If you can send me the link to the video too, so I can.
I will send it to you.
If
Thank
not,
you.
I can just look it up on your YouTube channel.
Okay. Thank you all.
Thank you.
Thank you.
Thank you.
Thank you.